So our next speaker is Laura Schulz, who is the professor and director of the Early Childhood Cognition Lab of the Brain Cognitive Sciences Department here at MIT. So Laura is going to tell us about what really matters, children's inferences about learning, trying, and caring.
Thank you very much. It's a real pleasure to be here. When Liwei invited me to give this talk, I said, Liwei, I don't actually work on early life stress. And she said, no problem, just go ahead and talk about it, whatever you'd like. And maybe because I don't work on stress, I didn't worry about this until about 10 o'clock last night when I looked at the lineup of the people who would be speaking here today. And I realized that I was really in trouble because the people who were speaking are some of my heroes. Many of the people in the room will not know me or my work, but I have seen Dr. Burke Harris's TED Talk and her phenomenal work. I know Dr. Hannah Tisha's groundbreaking work on lead and flint, of course, Dr. Shonkoff's work on the Center for the Developing Child, and of course, Jeffrey Canada's leadership in the Harlem Children's Zone. In fact, my partner came back raving last year about a talk he gave at the Camden Coalition. So this was an intimidating lineup, and I actually spent 7 years of my life between undergrad and graduate school working with youth at risk in direct service, in housing projects and after-school programs and mental health programs. So I care a lot about these issues. I've spent a lot of time thinking as a scientist how we can bridge the gap back to translational work, and especially how we can think of very early childhood learning as one of the key social determinants of health. It matters a great deal if you know your letters and your numbers before you go to school. But all that said, as a scientist, I don't work on these issues. So what am I doing here? And then I looked at the agenda again, and I thought, oh, maybe I know what I am doing here, especially in the middle of the day, having heard a lot of work on the profound and enduring effects of adverse childhood events, of poverty, of stress, of injustice, of trauma, of abuse, of lack of social support and social networks. I'm going to be your respite. I am going to intervene with a stress-free moment. Because I am going to tell you and try to remind you of what you already know, of what our babies, toddlers, preschoolers, children potential really is, how what our children are, how noble in reason and infinite in faculty. Because my research tradition could not be more optimistic. I study babies and children because they're the only organisms in the known universe that solve all the hard problems of cognitive science. They solve problems of facial recognition and natural scene understanding, problems of concepts and motor planning and navigation, problems of natural language acquisition and theory of mind and emotion understanding. And they solve all of this in the first few years of life. So I often find myself pointing out to other audiences a paradox today, which is that today we have incredible artificial intelligence systems that are going to drive our cars and that can beat us at Go and Jeopardy and that are the engine behind some of our most innovative corporations. And children should not drive cars, and they're very bad at Go and Jeopardy, and they have almost no market value. And yet children can solve a lot of problems that today's AI systems cannot. Children can't drive cars, but they can navigate their bodies through space with the sophistication and flexibility our roboticists can only dream about. Children can't recognize a million faces with high fidelity, but they can look at a single face, even one with a deeply non-canonical emotional expression, and tell you a lot about what that person is thinking and feeling. Children cannot look 20 moves ahead and Go, but they can invent imaginary possible worlds, literally as child's play. And when we talk about children's sensitivity to their environment, these are the kinds of skills that we are talking about, the things that make them strong and resilient and the things that make them vulnerable. I don't think I need to tell this audience that if we invested in these astonishing intellects at the rate that we invest in our new technologies, we would change the world. But it's also the case that if we want to understand human intelligence or reverse engineer it, we're going to have to understand what happens to all of us in those first few years of life. So today I just want to give you a flavor of the kind of work that I do, and it's basically to study the hard problem of cognitive science, which is the problem of induction, the problem of how, for better and for worse, we learn so much from so little so quickly. I'm going to show you work with both infants and older children. I'm going to show you older work and brand new work in the lab, all of it quite briefly. I'll start by showing you that 16-month-old infants can use just a little bit of data to make decisions about when to ask for help and when to explore. And I'll show you recent work suggesting that we can track in a precise quantitative way how children's exploration tracks with the difficulty of the problems they encounter. But children's exploration is also, as we know, affected by the social context, by what adults say, and also what adults do. And this affects how children explore and how persistent they are. Finally, I'll end by showing you a little bit of recent work showing how sophisticated infants' understanding of emotion is, vastly more sophisticated than I think any of us believed. If there's time at the end, I'll also talk about a few interventions we're trying. This is a little project on early STEM education, trying to bring some of what we know about the sophistication of early learning to early childhood learning. And I also am going to talk about a new method we've developed that I actually hope will be a resource for everyone in this room. Okay, but let me just jump in here. And I'll start by pointing out that we all have a problem, and the problem is that we're immersed in the world. And that might not seem like a problem, but like all problems, it's only a problem when things go wrong. And when things go wrong, it's a confounded setup. You may not know if you did something wrong or if there's something wrong out there in the world. And this is a crude cut of the hypothesis space, but it's very important in engineering as the agent state and the environment state, and education as locus of control. Am I not studying hard enough, or was the test unfair? It is a nice way of partitioning a complex space for further exploration, and it suggests very different courses of action. If you think you're doing something wrong, you should probably ask for help. If you think something is wrong in the world, you might want to go change the world. So we're going to ask here whether 16-month-old babies can use a little bit of statistical data to make these kinds of distinctions and choose to seek help or explore accordingly. So what we did in this experiment was we showed babies a bunch of toys, and then we showed them two experimenters. And in one case, the first experimenter tried to activate the toy and succeeded, and the next time she failed. And then the second experimenter tried, and the same thing happened. So even though we're here at MIT, evidently we have terrible toys, the circuit's a little loose, something's wrong. In this case, the data suggests that what's wrong is probably in the toy. It works probabilistically for everybody. And so when the baby themselves cannot activate the toy, maybe they should change the object. We can contrast it with a case where babies see the same pattern of success and failures distributed differently across agents. This time, one agent always succeeds, and the other agent always fails. Now, this is, again, a tiny bit of data. Just a couple of examples, the kind of things human learners are very good at learning at, even though our AI systems require big data. So this little bit of data suggests that actually some people can make this go and some people can't. So when the baby themselves can't make it go, they should say, oh, maybe I'm doing something wrong, and maybe they would be more likely to ask for help. So I'm going to show you a little bit of what that looked like here. You're going to see the two things happening in parallel, getting different patterns of evidence, and then you'll see what the babies do. And I don't seem to have sound up here. It's not critical for this study, but it will be. So you can just watch in this experiment. I'll need sound for others, but. So what you see is that the babies try very different things. So we're going to try try to get the sound up for some of the other videos in the show. Obviously, we didn't just test two babies, just a snapshot of one experiment. But what we found is that the distribution of babies' choices depended on this little bit of expression data, the rational inferences from the data to decide what to do. Any luck? All right, I'm going to be the voiceover as much as I can, because we'll just play back. Great. Okay. So you saw the baby's different behavior, and these are the results, so different patterns of successes and failures. So that was some old work with babies. What we've done more recently is try to get precise quantitative measures of how babies' exploration might track the kinds of problems they're encountering in the world, children's exploration. We did this in a ridiculously simple way. So in a department that can turn brains transparent and activate cells with light, it's a bit of an embarrassment to say that we did this with a box and some marbles, but we gave the children a box, and we gave them a problem. We said we're going to put either 9 red marbles or 3 green marbles in the box, and you get to shake the box and find out what's inside the box. So this is a fun, simple game. Children can do this. But importantly, we can contrast what they do when we hand them the box with a case where we tell them, okay, there's either 9 marbles in the box or 8 marbles in the box, and you can shake the box and find out what's inside. Now, importantly, it's the same box, right? There's 9 marbles in the box. If children's exploration is driven only by the sensory motor properties of their environment, they should shake this box identically. But what if children are really tracking is the difficulty of the discrimination problem of the thing they did not hear, right? But might have heard. Then this is a much harder problem. And they should shake the box much longer in the 9 versus 8 case than the 9 versus 3 case. And the beauty of marbles is we can do a lot of things, right? So we can test a whole range of contrasts, ranging in discriminability from really easy problems, 8 versus 2, 9 versus 1, 7 versus 2, to quite hard ones like 4 versus 3 or 9 versus 8. We can also get an objective measure of the psychophysics of these discrimination problems from adult subjects by looking at the mean and standard deviation of their judgments from the sound of how many marbles are in the box and what kind of overlap there is in their distributions. So adult psychophysics judgments are going to be our discriminability index, the negative log discriminability. What we're looking at is how long children shake the box. And remember, they only ever get to hear the one sound, the one marble. We're just looking at their shaking time here. So let me show you what it looks like. This would be much better with sound. We'll see if anything comes up. No luck. All right, well, shaking. So 20 seconds there. And here's another child who also has 9 marbles in the box, but a much easier problem. So remember, they have to be comparing what they do hear with what they might have heard, with what they could have imagined they heard, and how hard that problem is. I've been working on the relationship between play and learning my whole life, on how exploration and learning might track uncertainty in the world. I can safely say that I never get data like this. It falls out on a line. A couple of weeks ago, we pre-registered an experiment with 4 new contrasts. We made the prediction it was going to fall out in this line with a new group of kids and new contrasts. And I wish I had it here, but it just falls out directly on that line. So I've never been able to predict quantitatively how children are going to play with a box. But what this suggests is we are exquisitely sensitive to the statistics of environment, to the kind of learning we do, to how it tracks our exploration. This should not be a surprise. Infants learn to speak, right? Infants learn to speak and walk and plan right? And navigate and recognize faces and recognize your beliefs and desires. We take these things for granted because they're common sense. They happen to our babies and children. We think of them as intuitive. But these are remarkable cognitive processes, remarkable kinds of computations that are happening here. And we're, again, just beginning to understand a little bit about how these might be represented. But of course, exploration isn't just driven by uncertainty. It's also driven by the social context, things you learn. We're beginning to develop formal models of what it means to teach and to learn. We're beginning to be able to say things like, well, what would it mean to be a teacher? It would mean to provide the kind of evidence that a rational learner, on seeing that evidence, would draw the right inference, right? So if you take this data, this is what you ought to infer from the data, and a teacher ought to provide that kind of data, and the learner ought to assume that is what the teacher is doing. And when you make this kind of recursive inferences, you get a huge boost from the data you're seeing. You can make much richer inferences than if you just discovered the data randomly. So that, I'm not going to put up any of the computational work. I'll just say it makes predictions about why, for instance, if somebody asks you, how many states are there in the United States, you don't say 35. 35 seems crazy, but 35 is true. There are definitely 35 states in the United States. It's just not helpful, right? It just isn't likely to lead a rational learner to make an efficient and accurate inference. So you make all kinds of assumptions that let you converge on the judgment that when I say 50, I don't mean 51 and 52. The exception is in courts of law. When somebody says, how many sisters do you have? You say 2, and you say any more than 2, right? But in normal, helpful pedagogical communication, this doesn't happen. And this predicts trade-offs in instruction and exploration. If a knowledgeable teacher really demonstrates just one example of something or just one function of a toy, children should not engage in additional exploration. If there were more things there, they ought to have told you, just like I ought to tell you 50 states, not 35, right? But if you randomly come across the toy, or you're a naive demonstrator, and you happen to find one function, there very well might be more, right? There's no reason to stop exploring. Or if the teacher's interrupted in the middle of the demonstration. So you can get very different inductive inferences based on the same data, depending on how that data is sampled. So you can test this. We tested it with a novel toy with non-obvious affordances, but it did a lot of things. There was a squeaker, there was a light, there was music, there was a mirror. And we introduced the toy in one of 4 ways. We either did it saying, watch this, I'm going to show you my toy. That's very lightweight, but it says, I know about this toy, and I'm being a friendly, helpful teacher. Or we did it accidentally. I found this neat toy here. Oh, look at that. And we did the same demonstration. We only ever showed the squeaker tube. We showed it at baseline with no demonstration, or we did a pedagogical condition where we just interrupted right at the end. Say, oh, sorry, I got to go. I've got to go answer a phone call. I'll be right back, right? Which to suspend the inference that this was exhaustive, complete evidence. And in all cases, we can then watch how the child plays. If it didn't take so much time, I would now unplug so you really could hear the sound. I'm going to try to do the voiceover. I'm going to show you a child just in the pedagogical condition. Remember, they've seen only one function of a complex toy. There are many things this child could do. Watch what the child does do. I'm going to show you my toy. See that? It squeaks. And now she leaves the child alone. And the child squeaks and squeaks and squeaks and squeaks. And I sometimes tell my graduate students, if you ever find yourself doing this, stop and think. And that's all the child does, right? Now, when the experimenter comes back, she says, I'm going to ask you some questions. The child says, sure, I'm very smart for a 5-year-old. And then she begins to ask him about the functions of the toy. And of course, he can only demonstrate the squeaker. He doesn't know any of the other functions. And that's, in fact, what we found. So in a pedagogical context, children's exploration is substantially reduced. The important point here is the child is very smart for a 5-year-old. That's exactly the right inference you ought to make. The point of teaching is to constrain the hypothesis space. That is useful when you're right about what that hypothesis space is. It's much more efficient. But if you're wrong, if they're the unknown unknowns, if you're giving misleading evidence, then you will miss a large space of the world. It creates an inductive bias, which is what it is supposed to do. It's supposed to get you into the right space, but at the cost of other things that might also be true. So this is a built-in trade-off. We affect children's exploration not just by what we say, but by what we do. So this is a recent study with babies, and what we were doing in the study was asking whether babies could learn the value of effort from watching an adult experimenter. So we had an adult either succeed effortlessly at two different tasks and just repeat those tasks so that they played with the toys for 30 seconds, but they just repeatedly succeeded. Or the experimenter tried hard and struggled for the whole 30 seconds and succeeded only at the end. Then the child gets her own toy, and it's not going to work for the baby. Right? And the question is, what does the baby do? And the important point here is that the experimenter is doing two different goals with a whole set of different actions that have nothing to do with the child's own goal or the child's own action. She can't imitate anything the experimenter is doing, right? The question is, can they draw a rich inference about the abstract value of effort in this context, and does it affect how the babies themselves persist when they're given actually an impossible task? And this is work with Julia Leonard, who is sitting over there. So I'm gonna, again, show you this work lamentably without sound. I'm going to try to get this out. How do I get this out? Oh, within 10 seconds, she succeeds. And then she's going to repeat that again a couple more times because we wanted to match for time in the two conditions. And then she tries another goal. She's going to try to get the keychain off. She succeeds within 10 seconds and then repeats that twice. And here's a baby having seen an effortless success. The child's heard that this is a music toy, but not seen it activated. They've heard the sound. But the button doesn't work. It actually works by a secret button underneath. The child can't activate that. And she's out of here. We can compare this with a child who sees an experimenter trying hard before succeeding at her goal. So now she's going to try for the whole 30 seconds. And she finally succeeds. And then she does the same thing with the other goal. Again, a host of different actions, different behaviors, but again, demonstrating effort. And here's the baby. All right. So that we found that children who had seen an adult try hard before succeeding were more persistent than baseline, and in an effortless success condition, we pre-registered it and ran a replication of the experiment, found exactly the same thing. So from, again, just a very brief demonstration, children extracted the value of effort in this context. And I want to make, again, an important point. Both groups of children were doing the sensible thing. right? We all value trying hard and grit and persistence, but you can't try hard at everything all the time. And the children who saw somebody succeed effortlessly made the reasonable inference that toys in these contexts should be relatively easy to do, right? And the children who saw the adult persisting really hard and then succeeding made the reasonable inference that things are harder in this context and tried harder. I think it's critical in both cases, and we now know it's critical thanks to follow-up work, that the adults succeeded, right? So they did try hard, but it was followed by success. When adults fail with preschoolers, there is no difference in adult effort on children's success. They try at very low levels in both cases. So it's the interaction of the success and the communication of you're working hard at this, we're trying hard, that is boosting kids' persistence in these cases. And again, because I'm broadly interested in the problem of induction, I can't stress enough how interesting it is that kids are able to make this relatively abstract inference across different goals and behavior. This isn't imitation. There's nothing they can imitate in the behavioral level. They have to infer the value of effort across these studies. I'm going to show you a last study looking at children's understanding of emotion very early. So suppose I show you a scene like this. What's everyone looking at here? A sports game. There's no sports in that scene. Now, you made that inference totally effortlessly, but there is nothing in that scene. When we talk about natural scene understanding, we're not just talking about what you're looking at. You're talking about a causal representation of the things that generate what you are looking at. That's how human cognition works. What are they looking at? No baby. But that was a pretty good, pretty fast reaction time, pretty uniform response. What are they looking at? All right, you might reasonably and fairly suspect me of having swiped these images off of Google Images, and you'd be correct, and you might think, well, maybe those are particularly pedagogical, communicative images. So I took this picture of my daughter and her friend. What are they looking at? Scary movie. In fact, it's the moment the basilisk emerges from the Chamber of Secrets. So again, you don't see the scary movie, right? You see the reaction, and you infer things that are not in the scene at all. So there's a probabilistic, very nuanced relationship between events in the world and characteristic emotional responses. When you see baby, and it's nuanced, it's subtle. Because you can see a class of positive emotions, and especially in this room, if I put up a cute baby, most of you will think, ah. But I could also put up a beautiful scene, and you would have another distinct positive emotional response. I could put up fireworks, and you might have another response. Now, obviously, responses, these are probabilistic. You could have different attributions. You could have been up all night with your baby and been like, no, I don't want to see any babies. So you could hate fireworks, right? But in general, over the population, there is this probabilistic data, as with many things. We know infants are sensitive to the statistics of the environment. To the degree that infants are sensitive to this, maybe they have picked up something about the relationship between emotional responses and events that cause them. They're probable eliciting causes. So to test this, we chose an arbitrary class of stimuli that we think babies would find positive that differed very subtly. We're talking about the difference between amusement and excitement and empathy and sympathy. One of these is even a negative event, babies crying, but we thought that adults seeing it, unless they'd been up at 3 a.m., were likely to make a cooing, comforting response. So we had both objects and agents, all these classes, and what we did is this is totally critical that there's sound. I'm gonna have to imitate it, and this is disastrous, because this is what we did is we had people look at these, and we said, just make a nonverbal response. And so you heard things like hee, and ah, and oh, and ooh, and And I would be playing these for you if I had auditory sound, but since we don't, I'm just going to imitate them. And what we did is we could play then, we could present these stimuli, present the sound, and track babies looking. Right, so can they match the sound to the cause? Now again, this isn't cross-modal mapping. They're not mapping a happy sound to a happy face. They're mapping ooh to an exciting toy, and they're mapping ah to maybe a crying baby. Right, so they're mapping the cause of the emotion, not the emotional expression. So it worked like this. You might see this here and this here, and then we show them both, and I say ooh or hee, and you can feel where you might look, right? And in fact, when we did this with babies across a host of experiments, they do the same thing. They do it as early as 12 to 17 months. They are tracking the probable causes of others' emotional expressions. This could just be statistical mapping, but we wanted to know if they actually searched for and expected probable causes. So we looked into a box and we said, and if we pull out a fruit, that's not surprising. But if we look into the box and we say, ah, and we pull out a fruit, you should think there's something else in the box, right? And again, what you have to do that, you can't just associate the sound with the stimulus, right? You have to recognize that that is an incongruent, surprising event. Expect that there is another probable eliciting cause there. So we did this with, we can also look in the box and say, and pull out a stuffed animal. Now, that's weird, right? But it's not weird if you say ah and pull out a stuffed animal. So we can cross these events. We can also cross them with other contrasts. And in both cases, we found that babies searched more for the probable eliciting cause given this kind of data. So I need to stress that this is against a backdrop of research that has suggested that babies are sensitive to valence and arousal, the difference between positive and negative emotions, or maybe to 5 basic emotions: fear, surprise, disgust, anger, sadness, and happiness. But they are sensitive to the difference between excitement and amusement and empathy and anticipation, right? This whole range of emotions. And they go expecting and searching for these kinds of eliciting causes in the second year of life. So again, we think this is critically important. If you've been at events at our department for a while, you might remember that on the wall over there used to be an image like this that had perception, cognition, action in a big blank square. And we think emotion is a really important thing to put in that square and to begin to fill in the blanks of our kind of cognitive science. I want to end with just 2 other things. One is just a quick note about some of the things that we're trying to do to take what we know about learning in early childhood, which is that it's rich, it's sophisticated, it's powerful, it's abstract in all of these ways. And in other contexts, when I give this talk, I give the talk about the child, a scientist, and all the questions are, so why are our children so bad at science, and why is science so hard? And there's a lot of interesting answers to that. But part of it is, I think, is when we think about STEM learning in early childhood especially, we show children really hard things. We show them shadows. We show them balls rolling down trajectories. And you have to draw vector diagrams to know how a ball is going to run down a trajectory. And, I would defy most of the people in this audience to stand up and explain how shadows work with the optics of light, right? Those are things that are cool and demonstration, but they're very hard to understand the science, right? Very, very hard. By contrast, the kinds of things that we work on, like understanding samples and populations, understanding when evidence is confounded, understanding how to isolate variables, in simple contexts, those are actually intuitive. So we've actually made a bunch of little videos. I'll show you a little snippet of it. These are actually on broadcast TV now in, I can't show you a snippet because there's no sound. But in any case, it's a gumball machine. The ostrich has gotten all the pink gumballs, and Yana realizes that that is not a random or fair sample of the gumballs, right? If you were just letting gumballs fall out of the machine, you couldn't get all pink gumballs out of the machine. Therefore, you're not randomly sampling from the machine. The ostrich must be sneakily going ahead and choosing the gumballs. And we can use this to talk about samples and populations and random sampling and what you ought to get. And we know children understand this because we know babies understand this. We know babies have expectations about what sample you'll get from a population. They know when that is violated. They draw different inferences depending on the sample. We can use that kind of demonstration to start introducing the method and the ideas behind inquiry much, much earlier than we do now. I want to end with a couple of other things. We've had a fabulous partner across the street. All of our labs are on site at the Boston Children's Museum, so we go to the children instead of bringing the children in here. And I can't stress how fantastic they've been as a partner. And part of why we go there is they do try to draw from the community. They have a $1 Friday night. They have deep connections to Head Start programs in the community. We're trying to get a more diverse audience. But it is a tip of a very small iceberg. And there's a big problem in the work all of us want to do. And the problem is access to children. right? How are we going to do randomized controlled trials? How are we going to do interventions? How are we going to do all of these studies if you have to bring children back into the lab repeatedly, or you need collaboration from school districts that are already overloaded, or pediatricians' offices who have their, as everybody knows, their slates full with 20-minute visits, underpaid, and have to get through a whole bunch of assessments very quickly. So Kim Scott in my lab, a recent PhD, has developed an online developmental lab. This is not video conferencing. You can Google it, and you can participate in research at your convenience in your house. The studies are up online. You give consent through the video platform. You can choose your privacy settings. You can choose to upload your data. And it's an open source platform, so this will be available to everybody. And it will, I think, transform our work, because you will be able to get more representative sampling. You will be able to do reproducibility. You will be able to get rare populations. We oversample children with autism who are high functioning, because children with autism who already are at a lot of OT and speech therapy and physical therapy appointments do not need to come into MIT for scientific purposes. It can be stressful for the child and the parent. But in their home, when they're at a good time for testing, that's a different story. We lose 40% of our babies because they nap or they sleep or they, when we're trying to recruit them. But if they're in their home and the parent chooses the time of testing, what we know about this already from a couple published papers is this is demographics not from our usual Boston Children's Museum population, but from participants in a 3-year longitudinal study. We get dropout and attrition rates there. You can see we highly oversample from our highly educated Boston, Cambridge area audience. This is the US Census data, where most of the population has only a high school degree. This is the data we get on Looka. It looks a lot closer to US Census data. And we can replicate in case studies all the measures, preferential looking, coding. We could from videotape anyhow, right? So we can see when the parent is looking, when there's interference, in the same ways that we can in the lab. So I'm very excited about this endeavor. It's in beta development. We need to make it robust for users and families, but I think it's a hugely exciting innovation. So thank you very much.